Question 3 then. A student looks through a blue filter at a green leaf on a white background. Describe the colours that the student sees. Now do be careful with this because it says colours. You're expected to talk about more than one colour. A reasonable number of students only talked about the leaf. They forgot to talk about the background and what colour that looks like. Okay, well, through my twin skills in biology and art, here's the situation. Green leaf, white background. So if we look at this blue filter, what are these things going to look like? If we take the leaf first of all, green light's coming off the green leaf. We know that a blue filter will only let blue light through. It will absorb all the other colours, which is why it looks blue. So it will absorb green light. No green light from this leaf will get through that filter. So no light reaches us, it's going to look black. So our green leaf is going to be looking black. The white background, of course, light of all colours is coming from that. The blue filter will let the blue light through but block all the other lights, so all that will be left is blue coming through. So we'll have a blue background, black leaf. 2 marks for that, 1 for each of the things that you're looking at. We are now looking at a picture of people taken with a heat sensitive camera. Explain why the people can be seen against the background in this image. Again, careful with the wording. Why can we see the people against the background in the image? A lot of people talked about how the people are giving off heat or infrared radiation, but they forgot to contrast it with the background. Why is it that people show up against the background? Well, it's because the background is colder than the people. So, because the people are hotter than the background, 1 mark, they're going to be giving off more heat radiation. So they phrase it in the mark scheme as more infrared radiation at shorter wavelengths than the background. Remember, when we talked about things that are hotter, they give out shorter wavelengths and they give out more of them. So we've got a higher intensity, higher frequency, shorter wavelengths. That's the stuff that's being given off by the people compared to the background, which is colder. 2 marks for that. Moving on to this diagram here, we're going to need to get rid of our beautiful leaf. Apologies, art fans. We're going to see how we're getting our light bouncing off this mirror. We need to show the normal and we need to show the angle of incidence and the angle of reflection. So this is your standard mirror diagram. Here's our mirror. We use these hatchings to represent the non-shiny side of the mirror. We've got a light coming in, coming out. That's what we have so far, and they've even given us the arrows. So we need to show the normal. The normal is drawn at 90 degrees to the surface of the mirror. So the normal is going to look like something like that. There you are, there's your 90 degree line. So your normal's usually drawn with a dotted line, although they didn't specify that it had to be dotted in the mark scheme. But that's what it's going to look like, 90 degree line to the surface. Angles of incidence and reflection. Some people are looking at this angle here and this angle here. That will never be true. We're always measuring our angles from the normal. That's the point of drawing the normal in the first place. So this here is the angle of incidence because the ray is going in at this angle. This here is the angle of reflection because the ray is coming out at this angle. Notice how these 2 angles are exactly the same because I've drawn this so perfectly. The angle of incidence should always be equal to the angle of reflection. That is the law of reflection. It's just not particularly drawn particularly well, particularly there. So there's your 2 marks, 1 for the normal 90 degree line, 1 for the angle of incidence, the angle of reflection. There they are. Now this is where it gets tough. The ray is going in into a 45 degree glass prism, so there's your angle of 45 degrees there and there. That of course is 90 degrees. State what can be deduced from the diagram about the value of the critical angle for glass. Right, so for this you really needed to be confident with your ideas of total internal reflection, because that's what's happening, right? Your ray is hitting this boundary here and all of it is being reflected. So just to remind you very quickly, if I shine light in a semicircular block and I shine it at a certain angle like that, there's my 90 degree line, it will tend to refract out, and this will work if the material I'm in, the glass, makes light travel at a slower speed to how it travels in the air. So it's bending away from the normal, you can see that. It always bends away from the normal if it's moving into a material that speeds it up. If I increase this angle will increase as well. And of course I could increase it so much that the angle of refraction becomes 90 degrees. So let's say we shine it in at this angle. There we go. And we've shone it in at such a big angle that the angle of refraction is now 90 degrees. This situation is shining the light in at the critical angle. So this here is the critical angle. Sometimes at A level we give it a little IC to represent the critical angle there. Shining it in at the critical angle will give you an angle of refraction of 90 degrees. So it goes in, hits the boundary, comes out at 90. Now, if you shine it in at greater than that, we can't really get an angle of refraction that's bigger than 90 degrees because that would be inside the material. It wouldn't be refracting, it wouldn't be going into our new material. It'd be bouncing in here. So what we find is that if you shine it in at greater than the critical angle, it will just totally bounce off. It will totally reflect, and it will do that inside the material. So it will reflect internally, and that's why we call it total internal reflection. So if I shine my light in here, it will completely bounce off this surface here. We have total internal reflection. So the condition for total internal reflection is that we're shining the light in at greater than the critical angle. If you shine it in at the critical angle, it will refract at 90 degrees. If you shine it in less than the critical angle, it will refract out. If you shine it in at more than the critical angle, it will totally internally reflect. So, just for completeness, let's have a quick sketch of that. Here's our curved block. Bing, bong. There we go. So this angle here is greater than the critical angle, and as a result of that, it is reflecting. Again, these two angles are equal because we have reflection going on. So with all of that in our heads, we look at this situation, we see this is bouncing off here, so we know it's totally internally reflecting, which must mean that we're shining it in at more than the critical angle. So the critical angle must be less than this angle here. Now of course we measure that from the normal. If I just use my pen here to represent the normal, there it is, 90 degree line like that. So the critical angle is going to be less than this because we're getting total internal reflection, so the critical angle must be less than 45 degrees. Mark scheme says basically that for 1 mark. It's a 1 mark question. This last one, don't worry too much if you didn't get it. It was really horrible. Why high quality optical instruments use prisms instead of mirrors to reflect light? You get 1 mark just for saying it uses total internal reflection, which seems a bit weird. The second mark is to say that the light or no light is scattered. So when you've got light bouncing off a mirror, you've got a situation here where, here's my mirror, because the mirror isn't infinitely thin, you've got a layer of glass over the top, so the light sort of comes in and it sort of, some of it might bounce off the front of the glass like that, some of it might refract into the glass and then come out and bounce off like that, and all sorts of stuff might happen. You don't get that if you use total internal reflection, because it's not like the surface or the boundary of this prism here has any thickness at all, it's just a boundary. So you'll get all of the light bouncing off, no scattering. But again, don't worry if you didn't get that.